is there still anything to find out about this wondrous exponential number line? One thing that we haven't mentioned yet, but which kind of was lurking around the corner on many occasions, was this thing. If these powers of a are evenly spaced on this number line with respect to the exponents, why don't we just work on the exponents themselves? This is just a regular linear number line in disguise. This is 0, this is 1, this is 2, this is -1, this is -2, and there's a one-to-one relationship between all the points between these two number lines. And all we did when we multiplied powers together and took roots and all of that was just walking around on this number line, subdividing it, shifting around, multiplying, adding, subtracting, all of this. So this number line just carries the exponents. So any number x on this number line up here is in a direct relationship with the number a to the x. And this relationship, or this function, so x becomes a to the x, I like to write like this. So exponential function with base a, because its inverse is actually more well known, or has more of a proper notation, that is the logarithm to base a. The reverse function usually doesn't get a proper name, but it should, to really show the duality between exponentiating and taking the logarithm. And all the laws that we've learned about on this exponential number line, how powers work, are direct translations of all the algebraic laws that work on the regular number line. So, say for example, we've seen that a to the x times a to the y is a to the x plus y. On this line, it's just x plus y is x plus y. So actually, let's write this not in terms of x and y, but using variables for the numbers on the number line, a to the x and a to the y. So instead of a to the x, let's maybe give it a different name. Maybe let's call this uppercase x, and then there's some y here, and maybe let's write this y. So this is plus x, and this is times uppercase x. And then y, let's write it like this. And its corresponding number on the exponential number line, let's call this uppercase y, that is a to the lowercase y. So we get uppercase x times uppercase y is, what is it? Well, x and y are just the logarithms of uppercase x and uppercase y. So what's actually happening is that the logarithm of this product, so log base a, is what? It's just the sum of the logarithms. So log base a of uppercase x plus log base a of lowercase y, of uppercase y. What else have we seen? We've seen that going the reverse direction, that is multiplying with 1 over uppercase x, corresponds in the logarithms as subtracting this lowercase x. That is, the logarithm base a of the inverse of uppercase x is just the opposite of the logarithm of x itself. One thing that is maybe completely obvious is at this point is that the logarithm to base a of 1 is 0, and for good measure let's also add log base a of a is 1. And there's one last law for powers that we can translate into a law for logarithms, that is repeated multiplication with x, or just some scaled version. That is, if we take x and take it to the, let's say, rth power, in logarithm world, that would be just an r-scaled version of this lowercase x, that is r times log base a of uppercase x. And so all the laws for logarithms are just expressions of this duality between powers and exponentiation on the exponential number line and simple adding and subtracting on the regular number line, what's happening to the exponents. There's one last law for logarithms, the change of base rule, which we will look at in the next video, and you will really be surprised that it is just as trivial and it has just as much a geometric intuition behind it as all of these things.